Hello everyone, today I'm excited to introduce MicroDiffusion, our innovative method for medical 3D reconstruction from sparse 2D microscopy projections. This technology is vital in biomedical research and clinical diagnostics for analyzing tissue and cell interactions. Accurately reconstructing 3D structures from limited 2D microscopy projections is a major challenge. Traditional methods typically require costly hardware and involve lengthy data acquisition processes. Against this backdrop, we introduce MicroDiffusion, a novel technique that enhances the efficiency of reconstructing 3D models from sparse 2D images using implicit representation-guided diffusion processes. Figure A shows a conventional 3D laser scanning microscope. While it resolves depths effectively with its point scan data acquisition, it suffers from slow imaging speeds. Figure B depicts a stereo microscope using a non-diffractive laser beam, which achieves fast stereo imaging by projecting a 3D volume onto a 2D image, but lacks depth information in the resulting 2D images. Figure C demonstrates how our MicroDiffusion model, acting as a digital backend, enhances 3D volumetric reconstruction from the 2D projections shown in Figure B. This method significantly boosts volumetric imaging performance, balancing imaging speed with depth resolution. The aim is to reconstruct a 3D volume from 2D projections, using non-diffracting beams, with image quality comparable to that of traditional point scanning methods. Our approach has two main components: implicit neural representation, INR, and implicit representation-guided diffusion. First, we pre-train an INR to create initial, rough reconstructions. Next, we use 2D projections and 3D coordinates for classifier-free guidance in the MicroDiffusion process, integrating the INR output with the noisy images to guide the diffusion. INR methods use a function, typically a multi-layer perceptron, MLP, called FINR, to implicitly represent a 3D field. FINR maps 3D coordinates to predictive properties, aiding in allometric microscopy reconstruction. We uniformly sample 3D coordinates from volume M, and use the MLP to map these encodings to voxel density values. Reconstruction loss is assessed by comparing the mean squared error, MSE, between synthesized slices and the reference projection. To address distribution shifts during INR generation, we incorporate data from adjacent slices, using a Gaussian weighted average of neighboring slices to enhance inference accuracy. We utilize diffusion models to reconstruct 3D volumes, these likelihood models that can progressively restore data from Gaussian noise. In our MicroDiffusion, we train a classifier-free diffusion models with additional conditioning, C. This involves interpolating between conditioned and unconditioned model predictions to balance the guidance scale omega during generation. We use two encoders to transform 2D projections and 3D coordinates into conditioning information C, where projections provide content details and coordinates offer spatial context of the 3D volume, and we enhance the diffusion process by integrating outputs from the implicit neural representation, INR, as prior knowledge, specifically blending INR outputs linearly with noisy images XT before denoising. This method enables the diffusion model to utilize structural information from INR effectively, overcoming the challenge of limited 2D input projections and improving the generation of accurate 3D structures. We evaluate our methods using three metrics, PSNR, SSIM, and the dice coefficient, across three datasets. As shown in the table, our method performs well, capturing the principal structure of the original high-resolution model. The reconstruction results, randomly selected, demonstrate that our MicroDiffusion method produces reconstructions that more closely resemble the ground truth, particularly as the density of biological features increases. Our contribution is the development of MicroDiffusion, an innovative 3D reconstruction framework that transforms optical microscopy. By leveraging limited 2D projections with INR and DDPM integration, it rapidly produces high-resolution 3D images while maintaining detailed spatial information for analyzing complex biological structures. Demonstrating versatility across various datasets, MicroDiffusion establishes a new standard in machine learning-enhanced 3D microscopy, promising significant advancements in medical diagnostics and fundamental biomedical research. Thank you.